A linear search is very slow because it has to traverse the entire tree to find the data. A hash is a string or other types of data that you fold into a number. A hash table is a two-dimensional array pointing towards specific memory addresses of different points in the tree, and we use our hash number to index into that array. Okay, everyone, welcome to today's show, ladies and gentlemen, and members and subscribers, and everyone else. Today we're gonna do something fun. At least I consider it fun. We have been doing a lot of data structures and searches, and we have been working a whole lot with different measurings and stuff like that. But today we are gonna do the fun stuff. We are gonna optimize everything and perhaps make it the fastest database in the world. Who knows? Anyhow, we are going to create a hash table. And that's basically a very fast and very known a way of fetching data in an efficient way. But we are not going to do just any hash table. We're going to do the birch tree hash table. So I have decided to name this entire solution with my own implementation of an hash table and the binary tree that we have been working on. So that together is the birch tree. Since a birch tree is a very popular and beautiful tree in Sweden, I think it fits quite well. Anyhow, what is different between the birch tree and a regular good old hash table? Well, we are going to get into the details, but first I want to get going. Let's start coding and let's begin with a more regular hash table. Alright, so let's create our birch tree directory. And what do we need in here? Let's just very quickly create a makefile. And let's see, we need a flags, which let's do without optimization to begin with anyway. And wall is always good to have, setting the standard. Sure, why not? And yeah, that's basically it. And then LD flags, we have none at the moment. Perhaps we will need it later on. So we will have a file which will be called age table, and age table.c will be needed to create the O. And this is done by doing the cc of, let's see, of flags. And then we add the -c, and we need the source right here. Alright, and then in order to get the age table, and probably we won't have a binary file with a main and stuff like that when we're done. But it's good to have as an intermediate step in order to test things. So the actual htable binary will depend on the age table.o, if I can spell that correctly, .o, and we do the cc with the flags, and this time we're taking the source and we output to the target, and then we have the possible LD flags if we need it. I also like to create something which cleans up, and that will, as usual, remove all the O files and the executable. And then inside of the all, we just say that we need age table, like so. And the rest we can do from VS Code, I think. So in the tree directory where I am currently, I want to create a folder. Let's call, no, I do not actually. I shouldn't have created that while I was still logged in here. Alright, let's close this folder. And we go back to social path and let's see, birch tree. So it's best to take the whole thing, I think. So let's see, this is called tree. Open an editor. And this time we have that directory. Great. Alright, so no, all of these pop-ups, it's driving me crazy as usual. Let's see, inside of this directory we will need something like age table.h and something like age table.c. And at the moment, let's just add the name of the files. And this is htable. And this is htable.c. Like so, and I want to see on the left as usual. Right, let's see if it updated correctly. Seems like, and inside of here we should see everything. And if we do make, we only get an error because the main doesn't exist yet, but the O file was created as it should. So everything is working perfect. Let's set the home directory to the current working directory. And let's do some coding. Let's see, what do we need? I'm not sure exactly what we are going to need, so let's add all the standard stuff that I usually do, and let's clean up afterwards when we are done and have a functional project. stdio, and we need the uni std, and we also need std lib. We might need string.h. We will use a little bit of assert stuff, so let's include both assert and arrow number. And when we do that, we have to define this GNU source thing. And let's also take the std bool. And I want to create my own integers. So we need a type def unsigned int 32, and we need a unsigned tiny int, no, short int, and that is a int 16-bit integer. And then we have the unsigned char, which is an int 8, like so. Alright, but we will need some more stuff right here, because we will be dealing with ashes, right? Which means we need some kind of structure for that stuff. And I'm gonna design it. Let's see. I want something like this, I think. Let's make it a structure. So struct s ash and what will this contain? We will have a single integer, but not a 16 or 32-bit integer, somewhere in between. And I want to use, let's see, unsigned int, and let's call it hash, and I want it to be 21 bits of size. And why 21? Well, if we do, let's do it inside of the terminal. If we do something like, I think we need to do echo, and like this. If we have 2, and we take it to the power of 21, but we can't do it like this, because this caret symbol means something different. It's an XOR symbol. So instead we do the double asterisk. So 2 to the times of 21, that's all the possible combinations of zeros and ones, if we have 21 of them. So these are the number of combinations. And if we take that number and we divide it by 1024, we get 2 megabytes. So basically, if we use this kind of 21-bit hash, we have only added 2 megabytes of overhead to this hash table. So there will be some more stuff though, but that's why I think 21 is a good number, because if we were to do 22, for example, it will be 4 megabytes, and the entire stack has a limit. If we do ulimit, let's see, let's do flag ulimit dash s. So ulimit dash s. 8 megabytes is the maximum stack, and it's possible to change this, but then you need to be root, have admin privileges, and I'm not even sure that we're going to keep this stuff on the stack, but I think it's a good pointer to be below that limit. And I don't think we need more than 21 bits. If we do, we will alter this thingy. Alright, that was a little bit of a parenthesis. Okay, so now we have this data structure. Let's type def this. So type def struct s ash to ash, like so. And yeah, I don't think we need a type def for our ash table, because as long as we have this, we only need the type that we are storing in the table. So I don't see why we need to define that even further. Okay, so this is a good starting point. Let's do the function declarations as well, so we don't forget. We have an int main, which currently doesn't take anything, and that's basically it. Right, and what should this one include? Let's include our local age table.h, and perhaps we need to include the tree.h as well, but let's hold off on that for a bit. I think, yeah, let's focus on creating the actual hashing algorithm. Okay, so how should we do this? We need a function. Let's define the main first, by the way. Okay, so what are we returning from this function? Well, we are returning this, right? And we can return it as is. I don't think we need to make it a pointer. No, I think this is good enough. And what should we call this? We will have a couple of these different functions. So let's just call them like this. And these x's are what kind of algorithm we're using, because we will be using public algorithms for the actual hashing, but we will experiment a little bit on ourselves first. So let's call this first one naive, and then we will get gradually better ones. And we need some kind of input to this, so an int8 pointer with, well, let's call it input. And I think that should be enough. I'm gonna code this so it works for strings. It's possible to do it in a more generic way, and perhaps we'll do that at a later stage. But if we get this to work for strings, then it will satisfy our demands for our database. Okie doke. So let's say this input is a 0 terminated string. Shall we do that? Maybe not. It will be easier to convert this to a generic function if we send at least an int. Let's see, how big things are we gonna use as keys? Not bigger than 16 bits, I think. So let's call this size. And then we don't have to worry about null termination. And it's easier to change this to an arbitrary type later on. Okay, so how can we create an hash in a naive kind of way? So we have a string, right? Which looks like, well, this, ABCD. And what we need to do is we need to turn it into a number. And we need to turn it into a 22-bit int to be precise. So let's begin by defining this 32-bit int, and we do this with our hash type. And let's see, we can keep this on the stack, I think. And let's call it just hash. Right. So how do we turn a string into a number? We know how to turn a char into a number, right? Because a char is simply, well, it is a number if we look at the bits. And it follows the table of ASCII. So if we have a string of 4 chars, which this really is, let's turn them into individual chars to begin with. So we will have an A, a B, a C, a D, possibly a null terminator, but we are not caring about that since we have this size, and this will be 4 in this case. Okay, that's a good step 1. So here we take the string and we convert them to a list of char. This is a good way of representing that. Okay, so now we have a list of chars, and what do we do with them? Well, let's turn the A into the ASCII number representation that we talked about. So let's go into our terminal and let's see how we do that in the easiest possible way. I think we can use the Linux version of printf, and we want to show this as a let's do hexadecimal number, and new line. And is it possible to just do something like this? No, it is not. Okay, let's do this instead then. We do printf, and let's just do something like this. And A, B, C, D is what we have, and then we do a hex dump. Okay, so what we have is 61, 62, 63, 64. Alright, so we take it and turn it into ASCII and hex numbers. So this will be a list of numbers this time. Or maybe we do this. No. Let's do this. Alright. So now we have 61, 62, 63, 64. But we don't need 4 numbers. We need 1 number. And a very specific shape nonetheless. We need a 21-bit number. Right? But let's not worry too much about that at the moment. Let's think, how can we turn these into a single number? So we want our list of ints to go to a single int. What do we do? Well, we can just add them, for example. So we do 61 plus 62 plus 63 plus 64. And what will that be? You guys are probably better at counting in your heads. So let's see, we will have so 61 plus 62 plus 63 plus 64, but not regular numbers. These are hexadecimal numbers, which we denote by adding this 0x in the beginning. And that is not support. Oh, okay. We need to. Yeah, of course. This is printf. Let's do. So this will be a hexadecimal number. Percent dot 0. Let's just do percent x. And a new line. I almost introduced a format string bug there. Alright, 18a, or as I like to put it, 0184. So this is our result of the calculations. So our last step is sum equal to this. And we return it. Okay, so this is one way of doing it. And let's code this. We don't have to worry too much about this, turning a string into the list of chars and the chars into the list of ints, because C is handling that internally. C already sees all of these string characters as numbers, and how we represent them, if it's hex or binary or regular decimal numbers, doesn't matter much to the internals of C. So the only thing really is we need to sum them up. Alright, so let's do this in 2 steps, I think. Let's create a 32-bit integer h, which let's see, we will iterate through all of these string characters. So easiest way to do that is through a pointer. You know, I love those kind of things, right? So let's create an int8 pointer with a convenient name p. And we will also need some kind of a counter, int16 x. Okay, so this is our naive approach. We do a for loop where we begin by setting the p equal to the input, and we set x equal to 0. We loop as long as x is less than size, and at each iteration we simply do p plus plus, as well as x plus plus. And what do we do at each step? We set n plus equals, no, it's not n, it's age. Age plus equals p. So the character or the number representation that the character which is pointed towards, that is what we plus onto age. So let's zero initialize age. And yeah, this is basically it. Okay guys, let's continue with our program. So we are almost finished with this hashing function, but I do want to change it up a little bit. Instead of using this integer age, I want to go directly at this hash. So let's remove this. This was only temporary things. So let's see. We'll remove this age entirely. And instead, we are going to set the hash variable and its only member hash equal to 0. And then we have p equals to input x, x, p, x. And instead of using the age variable here, I am going to use the hash directly. And in the latest version, or perhaps not the latest, something like since C 11 perhaps, I'm not really sure, you can return a structure as a value. So let's just return this hash as if it was a pointer, but it's not. And inside of this main function, I'm going to make it take an argument. Let's update the definitions, by the way, so we do not forget. We have this, and it takes an int 8 pointer and an int 16 size variable, and we also need an int and a char double star, like so. Let's also create an alias, which I like to call these kind of macros. So this will take 2 arguments, and currently I want to alias it to our naive hashing function, like so. And this should be our naive version. And we can easily change this, define when we want to use another algorithm instead of this naive version. Alright, so what do we put inside of the main? Let's jump down a little bit so we have some space to work with. And let's begin by checking if argc is less than 2. Then we want to produce an error message describing our syntax. And the only, let me just do this. T. There we go. So the only argument we're going to take to this temporary main is the string of characters that we want to try to hash, basically. And we give it the first argv as usual. So that's the name of our binary executable. Okay, what do we do now? We need a variable. So we need 3 variables, by the way. We need a int8 pointer for the string, or we need, but we want. It will be easier to do this in steps, I think. We will have a int16 for the size, and then we will have the result in the actual hash, and let's call it age here to differentiate. So, and let's set each of these variables one at a time. We begin with str, and we need to cast this into an int8, and this is the argument, command line argument. The size will be the int16 representation of a regular string length, and we send the char variant of the str. And now we can execute our hashing function. So we do age equal to hash, and we send the string and the size, like so. And now we only have to print it out on the screen. So let's do it in, let's say, 5 hexadecimal characters. And we need to convert this to unsigned int, and it will probably yell at us anyway. And age is a structure, so we need to give it a member. And let's bring these together so it can be returned 0, like so. And then there we go. Oh, I deleted a little bit too much here, huh? Change to sorry about that sound. Well, let's do this manually. How many did I do? There we go. So let's see if this compiles, probably with a warning. No, not even a warning. Alright, let's see if it works. So we will run our age table, and it will tell us we need to bring it a string. Let's do hello, and then we get a value right back. And if we change only slightly, so MNOP, let's change the O to a P, then we see the hash changes from this to this. So it changes sequentially, because we are using the naive hashing algorithm where we just sum up all the numbers. But what the behavior that we are looking for is that when we change ever so slightly the input, almost everything should change in the entire number. Because the better our hash is at changing, the more probable it is that it will produce unique hashes. Okay? And that is what we are looking for. And that is also why this method, this naive method, is not going to work, basically. But we can use it temporarily to see how it performs when we compare it to the other ones. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Okay guys, welcome back. Before the break we managed to get this program to work. So we are able to create a hash from a string of characters. And if we type in a slightly larger message, something like this, we get a slightly larger hexadecimal number. But it all begins with two zeros, and that's not good, because we want to use as much as our variable space as possible each time. And that is why our naive approach, using this hashing function right here, it's not very good. But let's write something that is able to test how good it is. Because what we are interested in is the number of collisions. So a collision is when two different strings result in the exact same hash. And we don't want that. That will affect performance. So the less collisions an algorithm provides, the better. But let's go to the internet and let's search for English words txt, and let's see. No, not this one. It should be from a university or something like that. Here we are, University of Michigan. This one is good. So let's right click on this one and don't we have a copy link or something? There we go. And then we go into our working directory and we wget this file. Let's clean it up a little bit. I always begin by checking the beginning and end of the file. So head list. Let's change the name too, by the way. Never mind. Let it have this name. Okay, seems good. Here at the end there are two empty. We want to remove those. And how many did we get? 69,000. Okay, that's good. I will also open it up in VI, because then I will be able to see if each line terminates with a regular new line, or if it's this Windows variant, which might get us into trouble. Yeah, you see this Control M at the end. That's the Windows new line, or carriage return. So there is an excellent Linux command called call, which you just use like this. So you feed it the list and it will create a new list. Let's call it wl.txt. And then we open it up again, and this time it looks better. And if we go all the way to the down, we can remove these lines at the end. And if you're not comfortable with VI, you can use nano instead, like we did in the older videos. You can even open it up in Sociopath, actually, because it should automatically update. Let's see, where are we? We are inside tree and birch tree. Here is the word list. And here is our new one, WL.txt. So you have two choices. You can, now you only have one. You double click it. And then it open up in your default text editor. And if you scroll down to those spaces that were here before, yeah, let's do this one, and you save this file, then you will see Sociopath React and update the file. So that's one way of doing it. And let's remove the original one, the one without the txt, because we don't need that anymore. And I also want to create slightly smaller file with only the first, let's say, 50, 1, 2, 3, the first 50,000 entries, and let's put it into wl50k.txt. And let's check head on this file. Looks okay. Let's check tail. Still looks okay. And let's check the number of lines. 50k. Because it will make our calculations a little bit easier. So let's create 50k hashes, shall we? Let's create a function for that. This will be an example. So I have this convention, right, that I name all my functions which are temporarily, just for examples, with the prefix example. So let's see. We can make this an int32, and it will be example gen hashes. And what should we provide this with? A file name now to do it. Let's see. Maybe we should let it maybe we should save all those hashes somewhere. Yes, let's do an in file and an out file. So let's have two of these int8 string thingies. And I'm making it int32 so we can count the or int16 is enough. So we can count how many we succeeded in hashing, which should be all of them. Alright, so let's create this function. So we create an int32 and its example gen hashes, and we will have an in file and we'll have an out file, right? Like so. And we need this should be int16. Okay, so we need an int16 to keep track of the number of these hashes, and then we will have an in file descriptor. Let's just call it in, and I will make this a file with caps, so we can use fgetest and read one line at a time. It will make it a little bit easier, but when we come to the out file, I will use a regular file descriptor instead. Alright, so let's start by opening those files. So in will be equal to fopen in file, and we need to char encode that in file, and we will open this one up for read access, and out we will use regular open. And same here, we need to make it a char, and this is the out file. And which flags do we need? We need to have write only, but also create, so it creates the file. And I didn't forget the E at the end of create. It shouldn't be there. It shouldn't be there. And the last argument is just the permissions. So let's do 00644. That's so only the local user have right access. Why does it complain about my parentheses? I did one too many. Alright, like so. And then we assert that we have both in and out. And then we basically begin looping. So we need a hash, let's call it h. What else do we need? We need a buffer. And let's make it 128 perhaps. And what else do we need? Not much, I suppose. So we would do fgetS, and we will read into the buff, and we need to cast that. Read into the buff, and let's see. Then we have the size, and that will be 127. And then the file descriptor, which is the in file descriptor. And we want to loop this, so while this, like so. We will also need to zero out this one. Zero buff 128. Let's just very quickly create that zero function. So this is void 0, and it takes an int 8. Let's call it buff, and it takes the size, so size, no, int 16 size. And then we need an int 8 pointer, and we need an int 16 counter. And we do a for loop where we do p equals buff, and n equals 0. We'll loop as long as n is less than size, and at each iteration we will increase the pointer, and we will increase the n as well. And then the only thing we need to do at each iteration is zero out the current position. And then we are done. Let's create this as well. So we have void 0, int 8, and int 16. Like so. Okay, where were we? Okay, right here. We have read in the buffer. We also need a size variable here. So let's do size. So size will be equal to the int16 representation of string length, and we need to cast to char the buffer. So then we have, if we have A, B, C, D and a new line at the end, we'll have indices 0, 1, 2, 3, 4. And we will have the size equal to 5. So let's create a variable for index as well. We have enough space. So index equals size minus 1, and then we will index into this buff plus index, and we will set it to 0, and this is to remove the ending new line. So now buff contains what we want, the actual word that we want to hash. So let's make h equal to hash, and we send buff, and we send size. The size has changed. It has decreased by 1 because we removed this one. So we don't need that index. We can just do buff plus minus minus size. So we decrease size by 1, and then it'll be right, I think. And we will what should we do with this? We should print both of them to the file, and I will cheat a little bit and use dprintf here. It basically writes directly to the file. Well, it works like printf, but to a file descriptor of your choosing. And I choose out, and I want to print first of all the actual hash. So let's see how we did this. I think we did something like this, and then we put the word afterwards and a new line. And what do we have? We have an unsigned int, and it's h dot hash, since it's a structure, and the word is just buff, like that. We will also increase our n, basically just so we have something of value to return. We do also not want to forget to close our files. So we close out, and we fclose in. Return n. I think this should be enough. Well, let's try it out. We need to call it as well, by the way. So inside of main, so let's change this to let's see, we'll just do in file, out file. So if it's less than 3, we don't need str, we don't need size, we don't even need this. But what we do need, or at least want, are these in file and out file pointers. It's not really necessary, but I think it increases readability of the code. So in file equals argv1 and out file equals number 2. Then we run example gen hashes with in file and out file. And that's it. Don't think we need any message or anything. Or maybe we do. Let's do printf generating hashes ... And since we're not ending with a new line, we need to flush so we can see it on the screen. And then let's take care of the return value. So we return the number of hashes created. And we also need to do a security check, by the way. Because if size were to return 0, then this would be trying to index into the position before buff. And what's that actually? It should be, well, it's not on the top of the stack, so it doesn't really matter, I guess. But it can mess with this hash variable if we are unlucky. So we need to check for that. So if size is less than 1, we just move on. We also need to zero out the buff each time. And even here we need to do that. So 0 buff 128. Let's see if we can compile this whole thing. Make config is not the right one. make clean is. And jump, and we do make, and we get all of these errors. I think it just include files actually. Yeah, it doesn't find open, so let's do man to open since it's a syscall, and we need this annoyingly named file which is completely impossible to remember. So actually, let's do this. I'm sick and tired of that name of that file. So let's go into user include and see if it's in here. Yes, there we have it. And let's name it something else. Do we have something? Okay, the only open thing we have is OpenSSL. So let's symlink this file to open.h with a big O. So now we don't have to remember that annoying name. We should just be able to include open with big O.h. So we make clean and we jump down and we make. Okay. A colon instead of a semicolon, that's easily fixed. Warning unused variable h on line 18. Unused variable h. Did I forget the name of that? Let's begin there. 18. This is unused. But what is this then? Oh. And here we should have a semicolon too. Right? So let's try this again. Make clean, jump down, clear, and make. And warning pointer, target in assignment from char to int 8. Right, we need to cast those two as well. And then everything should be alright, I think. Let's see. So this should be an int 8. And this should be an int 8. Like so. And for hopefully the last time we do make clean, we jump down, we clear, and we do make, and boom, it compiles. So what did we name it? Age table. Great. So we run it against our 50k list, and the out file, well, out.txt. How to do it? Okay, 50k. So let's do head on the out file. Looks nice. Let's do tail on the out file. Alright. And let's count it. 50k. It works like a charm. Okay, so now we have 50,000 hashes. How do we figure out how many of them that are duplicates? Well, we could write a C function for that, but I would say it's easier to use this file and some bash commands, some Linux commands. So we know we have 50,000 of these. If we were to use the cut command, this basically means that we use the space as the separator and we grab the first field. So if we check the head of this file, we only get the hashes, and this is how it looks, really. So if we sort this and we remove all the duplicates, let's put it into a temporary file, no dupes.txt, and we check the head of no dupes, looks right, and the tail of no dupes. And what do we do now? We check how many there are. 2 no dupes. There we go. Okay, so there's only 1,600 left of those. Okay, let's just do this then. We take this number and we multiply it by 2. So these are basically how many of the 100k that are duplicates. And if we do 1, 2, 3, 4, 5, so 1, 2, 3, 4, 5. So then we have the index, and if we jump 2 steps to the right, 1, 2, here we have it. So 96.8% are duplicates. That is a really, really high number. And, well, we want to be somewhere 10, maybe 15%. This is almost all of them. And that's why our naive function is so bad. And why is that? Well, if we look at the out file, we take the head. No, we sort the out file. Then we take the head. So we sort the out file and then we take the head. So this is the beginning. And you see all of those zeros. That's kinda to expect in the beginning. But if we take the tail, then we shouldn't see any numbers with a 0 right here after the X. But we do. We even get 2 zeros. And each of these zeros is 4 bits. So 8 bits out of the 21 that we had from the beginning is not used at all, and perhaps even more. Let's check it again. Okay, it goes quite far into this one, but 8 bits we are not even using. So the next step, which will be in the next episode of this, will be to try to optimize this. First by trying to improve our own naive hashing algorithm, And later on, we want to try out other more well-known hashing algorithms and see if we can get this 96% down to a more suitable number, because the lower that number, the faster our database will be in the end. Okay, so please like and subscribe so you know when the next episode is out. Usually I publish a new episode every 4 days, and if you have any questions, please ask them in the comments. And thank you for watching, and thanks for today.